In this video, I will give you a quick introduction to complex numbers, and I've written here the complex number e to the I theta, and Euler's formula is telling us that e to the I theta is cosine theta plus I sine theta. Now, by definition, I squared is equal to -1. This is the imaginary unit, and this is the imaginary part of the complex number. This is the real part of the complex number. Now, I want to show you how you can represent complex numbers. So let's do, this is the unit circle. I have 0, 1, 1, -1, -1. And as we know, this is the cosine theta, and this is the sine theta. And this is a property of the unit circle. Now, I want you to take a look here at the complex number that I have, e to the I theta. I do have a cosine theta, and I do have a sine theta. So, one way to represent this complex number is the following. I can say that this represents e to the I theta, where theta is the angle between this line and the horizontal, the cosine theta axis. Now, I want to show you one more thing. When we have complex numbers and we want to find the magnitude squared of that complex number will be equal to the complex number times the conjugate of that complex number. And what I mean with that, so e to the I theta times e to the minus I theta, or using cosine and sine, I will have cosine of theta plus I of sine theta times cosine theta minus I sine theta. Okay, so what I mean with conjugate here, with this symbol, the star, I mean that wherever you see I, change the sign in front of the I. Now this will give you cosine square minus I squared sine squared theta, and then I also have minus I cosine theta sine theta plus I cosine theta sine theta, which cancels out. And from the definition of I squared is -1, with the minus becomes plus. And we know that from trigonometry this is equal to 1. So the magnitude of e to the I theta, this complex number, is 1. And this is why I have this line ending on the unit circle, where the magnitude is 1 everywhere along this along the circle. Now, the reason why I have e to the I theta on the unit circle is, I can make a note for you. So here, say I have e to the I theta. Okay. Whatever you have here, this will determine the angle theta, the angle that this arrow forms with the axis. Whatever you have in front of the exponential will determine the magnitude. In this case, because I have simply 1, okay, the 1 is implied. Because I have just 1 in front of the e, that's why I am on the unit circle. Let me show you a different example. So I'm gonna do another circle. Now, instead of 1, I'm gonna use, let's say that this is gonna be a 5, 5, minus 5, minus 5. I just want to give you an idea. If I have the complex number 5 times e to I pi over 4, then this would be, that would be represented with this. So z equals to 5e to the I pi over 4. As I said, the 5, what is in front of the e determines the size, the magnitude of your complex number, and what you have here in the exponent is what determines the theta that your arrow forms with the axis. Now I want to show you a case that is a little bit more complicated. So I want to do omega t. Omega t. And omega is a positive constant, so I'm using a positive constant. And I do have time here. Now, what does that mean? If you plug in t equals 0, then of course the angle that this complex number forms with the axis is 0. So at t equals 0, your complex number lies here. If t is a small number, you have just increased the angle that your complex number forms with the axis, so your complex number is here. If you increase t even more, then your complex number lies here. If you increase t even more, your complex number times here lies here. So as you can see, as you increase time, or as you wait longer and longer, your complex number is moving. It is moving on this plane, on this circle, and it's moving in this direction. Okay, and this will be repeated an infinite number of times. Now, if I make a small change, if I say, well, now I want to do 5e to the minus I omega t, then your complex number is doing something similar. You do start at t equals 0. Your complex number starts from here, but then instead of moving counterclockwise, after a little bit of time, your complex number is going to lie here. And then if you wait a little bit more, your complex number is going to be here. A little bit more, your complex number is going to be here, and so on. So if your argument here is a negative number, then your complex number is going to be moving in the clockwise direction. And this is a result of the fact that I have explicitly have t, time, in what determines the angle. So I can write it here. Theta is minus omega t, right? If my angle is determined by the time and it depends on time, then it makes sense that the complex number is going to be moving on this circle. And the last thing that I want to do, the last example I want to show you here, now I'm going to do delta, a constant, minus omega t. And you know what? I'd say instead of using 5, let's just use alpha or a constant. So a, delta, omega, those are real numbers. This is a complex number. Now the way that I will represent this, I'm gonna start. Let's draw a small circle here so that we can work on this. So I see that I have A here, so the magnitude of my complex number is A. This means this is A, minus A, minus A, that's my 0. Now, this is what determines the angle, and what I see here, at t equals 0, my complex number will be e to the I delta. This is at t equals 0. So what I'm gonna do, this is the A times e to the I delta, and this is where my complex number is at t equals 0. Now, I do see that I have a minus omega t, so as t increases, I expect that my complex number is gonna move a little bit clockwise. And as time increases even more, my complex number is gonna move even more clockwise. And then after a little bit more time, my complex number is gonna move here. So what this complex number is doing, at t equals 0, it is located exactly here, and then as time goes by, my complex number is moving in the clockwise direction. Again, this determines the magnitude of the complex number. This the delta shows you the angle at t equals 0, and this here is showing you that your complex number is moving clockwise. At what rate? How fast is it moving clockwise? This depends on omega. So omega is the rate at which your complex number is moving clockwise.